大家好，欢迎收看 Light 人物访谈的海外系列节目，我是 Light 期刊的科学编辑袁静泽。今天我们来到了瑞典顶尖的理工名校查尔姆斯理工大学，并非常荣幸地邀请到了来自微纳技术与纳米科学学院的奥萨 Haglun 教授，来同我们分享他在半导体紫外发光以及激光器件等领域的研究进展。本期嘉宾奥萨 Haglun 教授长期从事半导体面发射激光器的研究，近年来更是在紫外波段取得了多项突破性的研究进展，包括首次实现 UV 波段面发射激光器。2019年 Haglun 教授获得了由欧洲学术委员会评选的 Consolidator Grant， 该奖项是欧洲竞争最为激烈的研究项目之一。奥萨的成功获选，既是对其科研工作的肯定，更将进一步促进他与团队在紫外光电器件领域的深入探索与拓展。好，那接下来就欢迎观众朋友们同我们一起走进查尔姆斯理工大学，走进奥萨以及他的科研世界。
To make any UV VCSEL, you need to be able to combine materials that are good in emitting light in the UV with a mirror on each side of this material. The tricky part here is to combine the light-emitting material with highly reflective mirrors on both sides. A lot of researchers have put a lot of effort into trying to make mirrors out of the same material, so aluminum gallium. But that turns out to be very, very challenging and very tricky. Despite all these efforts, there are still no good mirrors made of aluminum gallium can provide reflectivity above 99%. And this is really needed for a good vertical cavity laser. What we have been doing is to take a different approach. So we circumvent these material limitations by instead using mirrors that are made of dielectric material, such as silicon dioxide and hafnium oxide. So then we have very high reflectivity mirrors. The challenge with this is that to have good light-emitting material, you need to grow that on the same material. But then if we want to put our dielectric mirror there, we need to remove that material we have grown everything on. So we have worked for a number of years on a special technique that allows us to etch away a specific layer selectively underneath. And by etching away this material, we're ending up with a thin membrane, you can say, of this light-emitting material. And then with this thin membrane, we can put a mirror here and a mirror here of our choice. So then we don't need to use aluminum gallium nitride for our mirrors, but we can use dielectric materials as our mirrors because of the special etch technique. When you do this removal, you need to have a very accurate control of the thickness of this light-emitting material, because that will set your lasing wavelength in the end. So it cannot vary by many nanometers in height. This membrane technology that we have developed that allows us to lift off the light-emitting material from the material it has been grown on, that can be very good for VCSELs, for vertical cavity lasers, but it can also be very beneficial for light-emitting diodes to increase the poor light extraction efficiency. So we can lift off the light-emitting material, we can structure the material and improve the light extraction efficiency. And this is also technology that could be beneficial also for high-power transistors. So you can lift off your transistor, the substrate it has been grown on, and you can place it on whatever heatsink you want. So this is a technology that does not only apply to VCSELs, but that can actually be used in many other fields as well. When it comes to blue VCSELs, there is still a big question mark is what is the best approach for the mirrors? So there are many concepts being explored in parallel. Dielectric mirrors, epitaxially grown mirrors, porous mirrors or air gap mirrors. What we now are offering is one more alternative, with the benefit that by using these high contrast gratings as your mirror, you can provide very high reflectivity that is needed, so above 99%. But in addition to that, you also get a mirror that is polarization selective. So if you have your grating bars, depending if your electric field is polarized in that direction or in that direction, it will experience different reflectivity from this grating. So we can enforce the laser to only laser at one polarization state. And then some applications really require polarization stable devices. The concept of a high contrast grating as a mirror also allows you to tailor the emission that comes out from the device in new ways, and that is still to be explored. So today we have ultraviolet LEDs, and they are becoming better and better, but some applications require different light sources, more well-directed beams, higher output powers than the LEDs can offer, and a laser would be such a light source. We are working on vertical cavity lasers because we think that they can offer these properties that we're looking for. So if we can make a vertical cavity surface-emitting laser array emitting in the ultraviolet, they can provide you with well-collimated beams with a lot of power compared to the LEDs, which would be very useful for sterilization applications, for example. But also in applications where VCSELs are today used in the infrared to cure plastics. If we instead could make a VCSEL array in the UV that can be used to UV cure materials. So you can have a very nice, basically a lamp where you can tailor your emission pattern and do that in a very efficient way. UV light can be used for sterilization to sterilize surfaces, air or liquids, the skin. If you go to really short UV wavelengths, so around 230 nanometers about, the penetration depth into the skin becomes really shallow. So you can actually directly illuminate the skin without damaging it. But if you have a wound with bacteria that is antibiotic resistant, it's really hard to treat nowadays. So an alternative method to treat that could actually be with UV illumination. So today we have only demonstrated optically pumped devices under pulsed conditions. And if this is going to be a useful laser source in the end, you want this to be electrically driven and continuous wave operated. So you don't want to have short pulses of light coming out, but you want to have continuous light coming out all the time. One big step to overcome is how to get these devices to become electrically driven. The materials that we use, the aluminum gallium, they are electrically conductive, but the electrical conductivity is not very good. So there's intense material research going on to understand and also improve the electrical conductivity in these materials that will benefit the development of electrically driven UV VCSELs in the end. We believe the way to get to electrically driven UV VCSELs is by using a concept that is called tunnel junctions. So what it does is that it allows us to use N-doped material on the top of the device instead of P-doped material, in which it's much easier to spread the current in the horizontal direction. Tunnel junctions have been shown for ultraviolet LEDs, but not yet for VCSELs. So VCSEL poses more different criteria on the tunnel junctions than the LEDs does. If the UV VCSELs are going to be used in industry, we also need to be able to offer different wavelengths of the devices. So in our group we demonstrated a UVB VCSEL around 310 nanometers. Xiamen University have shown a UVC VCSEL, slightly shorter wavelengths, but we still need to push it even shorter to span the full ultraviolet spectrum. So there is also work that needs to be done in covering more wavelengths than we are now. We are striving to make electrically driven UV VCSELs. So we managed to demonstrate the first UVB VCSEL, optically pumped, which was the shortest wavelength at the time that anybody has ever shown. Now we're trying to go for electrically driven devices, and we're also trying to get to even shorter wavelength lasers, but also to make electrically driven devices. So a device that actually will be used in industry in the future. It's a true honor to be offered such a very prestigious grant. Of course, it means a lot to me. It means that I can focus on the research that I have chosen for 5 years. So it's a quite long time span, I would say. And since it's a considerable amount of money, I can really focus on the topic and we can work hard to realize our dream, which is an electrically driven UV VCSEL in the end. You should focus on an area that you believe in, but also an area where you find that you have a competitive edge over your competitors, so you can write good proposals and get the funding that you need to get started. You need to try to keep a positive spirit throughout, no matter which rejections you get of article submissions or research proposals or so, because you're also the leader of your group, so you have to motivate your team players to still believe in what you believe in. I would also recommend you to try to identify and use good mentors. There are many people around you that can help you to boost your CV or the way you write about it. They can help you to read your research proposals. They can help you to have strategy discussions about your research. You just have to find these people that can help you. It could be people you collaborate with. It could be other teachers at the university. If you want to start something new in a field where you've not worked before, then it will take time to build your network, to get the material you need, and to develop everything, and to build up your lab, and yeah, it's about 10 years.
During the interviewing, we noticed an artwork with a high scientific science in Professor Ossa's office, and we learned that it was actually a teaching display tool made by Ossa herself.
So this is a crystal model I designed. So you can see how the small balls, or the atoms, make a perfect crystal here. But then it's not so perfect up here. So there are some holes where there should be atoms and there are no atoms. So to make even better materials, we can apply a bit of energy. So we should do this. You can see it changes, or we can shake it a bit. And then it changes, and now we have a very big, perfect crystal here, and over here, and here, and then just some line defects here, perhaps. So it's a good illustration to tell the students how a crystal should be grown or not grown, perhaps.